All right, folks, we're back to talk about the convergence of series of positive terms again. This is the second part of this section, and I just want to remind you of what we did last time. We looked at two different tests. We saw the integral test, and we saw this t-test, or the p-test for p-series. So we've got these p-series, and we have a condition for when they converge. Those p-series will converge when p is bigger than 1. And then we saw this far more general integral test, and we did some examples with it. I'm going to do one more just to start today to remind you. We want to determine whether this series converges. And we can just write out some terms in this. You know, we're plugging in, the first value we're plugging in is 1, so we start with a half as the first term, and then we're plugging in 2. 2 squared is 4, so we add 1, we get 5. The next term is 3 squared is 9, add 1, we get 10. And so here's the infinite series that we're going to get. What have we got? 4 squared is, so I think that's 17, ... Mathematicians always use 3 dots, by the way. You should always use 3 dots to denote that this continues forever. If you don't put the dots, it implies that it stops. And these are infinite series, they go on forever. The sum goes off to infinity, you can see there, my badly drawn infinity. So we can answer this question maybe by looking at the corresponding integral. So the integral here is going to be the integral of f of x, where f is given by the terms. The terms here are 1 over n squared plus 1. And so we're looking at the integral from 1 to infinity of f here, which is, in this case, 1 over x squared plus 1. And so we're looking at that, but it's only useful if we're certain that f is positive, decreasing, and continuous. Hopefully you can see that's always positive, the square is always positive, and it's always continuous for all real numbers, so therefore it's continuous for x bigger than or equal to 1. We actually only care about x bigger than or equal to 1 because that's what we have in the theorem, and the reason we have that is we're starting here. It corresponds to this starting value, the first value there. The other thing we need to know is this function increasing or decreasing, which means we need to look at the derivative. And the derivative of this, well, it's going to bring a minus out. The derivative of the denominator is 2x, and then we're going to end up with x squared plus 1. And that's definitely less than 0. We want it to be decreasing, remember. It's definitely less than 0 when x is bigger than 0. If x is negative, then this thing is positive. But what we need is that thing to be negative, in other words, f to be decreasing when x is greater than or equal to 0. And that's, greater than or equal to 1. And that's what we got. So what that tells us is that f is decreasing for all x bigger than or equal to 1. It's also decreasing when x is greater than 0, but we don't care about those extra points. We've met all the rules now. We've shown it's continuous. This is my abbreviation for continuous. We've shown it's positive, and we've shown it's decreasing, and therefore this integral will tell us about the convergence of the series itself, which means we need to do that improper integral. And this is an integral we can do because it just gives us an inverse tan. And so the limit here is the limit as r goes to infinity of the inverse tan of r minus the inverse tan of 1. I don't know what the inverse tan of 1 is, but it's some perfectly well-defined number, right? So this is just some value, some real number. It's defined, that's the important thing. So it's the inverse tan of r that we need to work out. What happens to inverse tan in the limit? Well, if you think about inverse tan, the graph of inverse tan looks a lot like this, and it asymptotes to pi over 2 and minus pi over 2 as you go to infinity and minus infinity. And so this value here is settling down on an asymptote of pi over 2. So that value is pi over 2 minus the inverse tan of 1, whatever that is. But this is a real number, right? This is some real number. What that means is the integral converges. That's a real number, so the integral converges, and therefore the series converges because we're using this integral test. We've shown that the function we're dealing with here satisfies the 3 conditions of the test. We've shown that the integral converges to a real number, and therefore the corresponding series also converges. So let's look at some other ways that we can determine whether a series converges or diverges. Okay, so our next theorem here, which helps us decide whether series converge or diverge, is called the direct comparison test, or I'll often just call it the comparison test. And what it says, ignore all of the details for a second, apart from this condition. It says that if I've got a series and these numbers are positive, and I've got another series that's also positive, but they're always bigger, so the series of numbers B are always bigger than the numbers A, then if that list of big numbers, when I add them together, converges to a finite value, then so must the list of small numbers, right? So we're looking at a series. And so I've drawn them here. You can see these yellow dots are meant to represent the series A. So here's A1, and here's A sub 2, here's A sub 3, this is A sub 4, there's A sub 5. And then the white dots are the values of the B series. So B sub 1, B sub 2, B sub 3, B sub 4, B sub 5. You get the idea, right? And the B's are always bigger. And if the B's are always bigger, but I add them all up and I get a finite number, it doesn't diverge, it doesn't go to infinity, then when I add up a smaller bunch of numbers, they must also converge as well. That's all this one says. So if I add up a bunch of bigger numbers and it converges, then that list of smaller numbers, when I add them up, must converge also. Very straightforward, right? And then the second piece is just the other way around. If it turns out that I add up the small numbers, and that list of numbers, when I add them up, goes off to infinity, then when I add up bigger numbers, that must also go to infinity as well. So when I take the smaller numbers and add them, and that series diverges, then the list of the bigger numbers, when I add them together, that must also diverge. So it's just the other sort of coin. One is I've got a convergent series above, and so anything below is going to converge as well. And the other one says I've got a divergent series below, and so anything above has to converge as well. Diverge as well, I'm sorry. Now, just here to the technicalities, it says suppose there's a number m bigger than 0, and so I'm going to put my m here. Here is my m. All this is saying is suppose this isn't the way things were set up for the second term. Suppose for the second term, and the second term only, A got really big, but B was small, right? So that violates our rule. A sub 2 here is not smaller than B sub 2. So there's a problem with our rule there, right? This doesn't satisfy that condition. What the m is about is saying as long as it eventually satisfies it, so in this case, for all values of n bigger than or equal to 3, this is true, right? For all values of n bigger than or equal to 3, B3 is going to be bigger than A3, B4 is going to be bigger than A4, B5 is going to be bigger. It's not true here at 2, but as long as we're talking about values of n that are bigger than or equal to 3, then the condition it holds, right? And so what I'm saying here is m is 3. So I'm allowed to violate this rule for a few of the early terms. That's what's happening here. I'm adding together an infinite number of things. And so what's really important is all of the numbers at the end, right? I can violate this rule for the first 100,000 million terms. But as long as after that I always obey the rule that the A's are smaller than the B's, then this theorem is true. Because no matter how many terms I violate it for at the beginning, eventually it holds from there on, and there's infinitely more after the point where it starts to hold, if that makes sense. So it's a technicality, but as long as you can convince me that the theorem is eventually, or that this condition is eventually true, then this theorem holds. So why is this interesting? It tells us whether one series converges or diverges based on whether other series converge or diverge, and we have ways to check other series. In the previous section, we had the geometric series test. So if we've got a geometric series, we can easily determine whether it converges or not based on the value of r. We also saw that if the limit of the terms doesn't go to 0, then the series is going to diverge in the previous section. The integral test lets us test series if we can do the integral of the corresponding function. We've got a p-series test. If we've got a p-series, we can compare with that. If all else fails, we can look at the limit of partial sums of one of the series, and if we can do something with that, we can use that to compare with the other series. So let's see how I can take all of these ideas and combine them in kind of examples. All right, so our first example, we're going to look at this series of sine squared n over n squared, and we're going to ask if it converges. So what we need is something to compare with, and this is a bit of an art to think about where we're going to get a comparison. So if I think about sine, I know that sine is between -1 and 1. So when I square it, I must get a value that's between 0 and 1, right? So sine squared of n has to be between 0 and 1 for every value of n. And so if I divided that whole thing, and we've done something similar to this before, but if I divided that whole expression by n squared, then I get the terms that appear in the series up there, and I also get a comparison. We can look at this inequality, and we can compare it to this inequality, and we can see that this is true for all n, and in our case we only really care about n greater than or equal to 1, because that's where the series start. But this inequality is true for all n. So in other words, we're adding up a bunch of terms, but all of those terms are less than or equal to the corresponding 1 over n squared term. So what I'm saying is, this is the series a sub n we're interested in, and this is the series b sub n that I'm going to compare with. Think about the series b sub m. The series we get by adding the terms 1 over n squared, adding the terms b sub n. That is a p series with p equals 2. And p equals 2 is bigger than 1. And so it converges. So when I add up these terms, I will get a convergent series. I'll get a number. And I avoid writing the word it, because there's several its going on in this question. Do I mean this series? Do I mean this series? So I'm always going to spell out exactly what I'm talking about. So what I've done here is build a comparison. I've built this inequality, and this inequality says the terms I'm adding up are always smaller than the terms that I have in the series 1 over n squared. But I know that the series where I get the sum of 1 over n squared, I know that converges because it's a p series and p is bigger than 1. And so it must be convergent. So the a's are smaller than the b's, right? The sine squared n's over n squared are smaller, less than or equal to 1 over n squared. And this comparison series converges, and so therefore the original series must also. And that's using this direct comparison test we've set up in inequality that's true for all n greater than or equal to, well, 1 in this case. And we've shown that the comparison series converges, and therefore by this direct comparison test, the series that we're interested in also converges. And when you set this up, you should do them in this way. You should lay out all of the pieces. Again, to get full points on questions, you're going to need to lay out all the pieces like this. On web work, you might not need to write a lot down, but I encourage you to write a lot down because you need to get used to actually using these ideas. So let's have a look at another one. All right, so our next one, notice I'm starting the series here at 2. Because if I started it at 1, it would have a division by 0 in the first term. So we're not allowed to have that. But that makes no difference. This is equally valid if all of these series start with 2. Speak of pen, you can see. If I start with a 2 there, then this whole idea is equally valid, right? Or in fact, if that's a 1. Because think about the difference. If I think about the series n equals 1 to infinity of a sub n, that's the same as taking the first term and then adding on all the others. So starting from 2 and going to infinity. Right? And this is an a sub n. This is an infinite number of terms. This is a single number. So pulling out a single number like that can't affect whether the whole thing converges or diverges. Because what I'm saying when I'm talking about converge and diverge is I take this infinite list of numbers and add them all together, and do I get a finite value or does it go to infinity? So no matter how many individual little terms I pull off at the beginning, I can't change that overall conclusion because I'm just essentially writing down a number and then adding up all the rest. And writing this one separately is not affecting whether all the rest converge. So that we can play a little fast and loose with the starting point is what I'm saying. So in this case, we're again going to use the direct comparison test because this series is not something that we recognize, right? When you look at these series, you're going to have to get into the habit of saying, okay, that's a p series, that's a geometric series, or that's almost a p series. This is almost a p series because the square root of n minus 1 is very much like the square root of n. Well, actually, it's always smaller than the square root of n, right? For all n greater than or equal to, well, we care about 2 here, so I'll just go with 2. This has to be true. I think everybody agrees with me. I start with a number, square root of n, and I subtract 1. So it has to be then smaller than just the square root of n by itself. But I can rearrange that and divide both sides, so I can write this. I can divide the square root of n over here, and I can divide the square root of n minus 1 over here. And so what I've got, right, I divided this one that way, and I divided that one this way. I could rewrite it the other way around. 1 over the square root of n minus 1 is actually bigger than 1 over the square root of n, just writing it backwards. And that's true for all n greater than or equal to 2. And I can't start at 1 because I'd be dividing by 0. There's a lovely box. And there's an inequality. So we actually see that, if you like, which way should we look at it? We can look at it this one. This one maybe matches what I had up there better. The smaller series is a p-series. The smaller series here, this is a p-series with p equals what? Well, the square root of n is n to the power of a half, so this is p equals a half, and that's less than 1. And so the p-series corresponding to that term diverges. Right? It follows from the p-series test that the summation of 1 over n to the half diverges. But the numbers in those terms are always smaller than the numbers in the series we want. And so we've shown that this thing diverges. Right? In this case, because the smaller one diverges, so we can put all of that together and just laying it out exactly the way the theorem's worded, laying out the inequality, since 1 over the square root of n, it's always positive, but it's less than 1 over the square root of n minus 1, and if it's less than, it must be true that it's also less than or equal to. If you're worried about that inequality, then you can just put an equal to sign there. If it's less than, it's definitely less than or equal. That's true for all n greater than 2. So this summation diverges. You know, I'm thinking about starting at 2, but I didn't write that down. It diverges because it's a p-series. P is less than 1. And it follows, therefore, from the direct comparison test, using this second case, that because the sum of the 1 over root n's diverge, this one, which the terms are all actually bigger, must also diverge, right? And again, I could write n equals 2 to infinity in there. So again, using our direct comparison test and the ideas we've got about p-series and that kind of thing, we can decide whether more complicated series converge or diverge. We don't know what they add to when they converge, but we do know whether they converge or diverge. All right, so here's another series. Our job in all of these is to build a comparison series. So we've got a series we're interested in. We want to find something to compare it to, and that something should be something we understand. And in this case, when I look at it, it says to me that this is a series that is related to a geometric series. Think about writing out the terms of this, and hopefully when you look at it, it reminds you of a geometric series. It reminds you of a geometric series without that 1 in the denominator. Because remember, the defining quality of a geometric series is that moving from term to term, all you're doing is multiplying by a number. We call that number r. And so going from there to there, all we did was multiply by a third. Going from there to there, we multiplied by a third. We multiplied by a third. I can factor that 2/3, that first term out, and what I'm left with is 1 plus a third, and then we'll get a third squared, and then we'll get a third cubed. And so this is precisely a geometric series where that the constant is 2/3, and remember the ratio here is 1/3. That's the ratio that we get moving from term to term. And this converges because the absolute value of that ratio is less than 1. And that was our condition for convergence. And so we can immediately say that that thing converges. And in fact, remember, geometric series, we know what it converges to. It always converges to c over 1 minus r, which in this case is 2/3 over 1 minus 1/3. So that's 1. So this thing adds up to 1, in fact. But that's not terribly interesting. What we're interested in is that it actually converges at all. And now I've got to think about whether that helps me. Because all of that analysis I just did, it may not actually help me with this series up here. Because I need to build an inequality. So one way to deal with this is think about the denominator. The denominator here is 3 to the n plus 1, right? And that's clearly going to be bigger than 3 to the n. Or put another way, 3 to the n is smaller than 3 to the n plus 1. Hopefully you can see that. And if I then divide those terms across the inequality because they're positive, then I end up with this. We get this inequality. This is true for all values of n, certainly greater than or equal to 1, which is where we start here. We've got this nice inequality, and that's what we need to be able to use the integral test. Right? So in this case, 1 over 3 to the n plus 1. Those numbers are always going to be smaller, positive but smaller, than 1 over 3 to the n. And I expanded my inequality just to note that it's always greater than 0, greater than or equal is still a true statement, and it's always less than or equal to this. And I know that the summation of that 2/3 to the n converges. Well, hang on, I don't have the 2/3 yet, but I can just multiply this whole inequality by 2, right? I can multiply across this inequality without changing anything and put a 2 there. So now I've got 2 to the power of 3n. When I add those terms up, it converges. These are all smaller, therefore the integral test tells us that the series we're interested in must converge. Sorry, I meant by the direct comparison test. So again, I'm just laying out, here's the inequality. the terms we're interested in are positive but smaller than the terms 2 over 3 to the n for all n greater than or equal to 1. We know that the series of this form converges because it's a geometric series with r as a third and they converge. And so by the direct comparison test, the series we're interested in converges as well. And so again, this is the idea. We're just laying out the idea, the pieces that we need to apply the direct comparison test. And here the key piece is this inequality. And you just have to play around to find the inequality. Try and work out something that looks like it might be a useful comparison and see if you can build an inequality and then decide what that series does. The direct comparison test isn't the only kind of comparison test we're going to look at. So here's another comparison test that's actually really useful. Our final comparison test for this section, I know there's a lot of stuff in this section, so you need to get down and practice it. But our final comparison test actually says that if you look at the limit of the terms of two different sequences, then you can actually link their convergence together. So let's look at this first one. It says if this limit is positive, then, I mean, we're looking at positive terms, right? We're looking at sequences with positive terms. So A's and B's, they're always positive numbers. So that ratio has to be either 0, infinite, so limit doesn't exist, or that limit is just some positive number. So this is some positive finite number. This is all this is saying. If this is some positive finite number, then these two series converge or diverge together. So what this is saying is that both of these series do the same thing. If this limit exists and it's a finite number greater than 0, and the sum of the A's converges, then the sum of the B's converges. If the sum of the B's diverges, the sum of the A's diverges. So they're absolutely linked together. They have the same behavior. And the way you can think about that is, if this limit is a finite number, yeah, suppose that limit was 2, right? Suppose for a second that limit was 2. So what we're saying is that when n is large enough, the ratio of those two numbers must be about 2, right? Eventually, when n is large enough, if the limit is 2, then eventually when n is really big, that ratio must be pretty close to 2. So a sub n must be twice b sub n. So imagine adding up all the a sub n. What you're going to get is probably something that's about twice the b sub n, right? So this is just twice b sub n. So I can just factor that number out. So the sum of the a's and the sum of the b's are going to be, closely related. There's lots of terms that aren't, they're not going to be equal like this because the terms at the beginning might be doing crazy things, but eventually you're going to get enough terms where one's just a multiple of the other. A sub n here is 2 lots of b sub n. Generally it would be L lots of b sub n. And so there's going to be a link between these two. Maybe we could factor a constant out. So if this one diverges, this one must diverge as well. If this converges, this one must converge. They won't converge to the same value, obviously, but you would expect them to both converge or diverge. That's kind of intuitively what's going on here. In this second case, if that limit goes to infinity, what that means is A is getting really big compared to B. So if the values in the series A are getting really, really big as you go along, and yet that series still converges, then the smaller series B must converge. So similar to the ideas we talked about before. In the last case, if the limit goes to 0, it means the b sub n's are getting really large compared to the a sub n's. So the b sub n's are getting really large, but yet when we add up all the b sub n's, we still get a finite number. So when we add up the smaller values, the a sub n's, we must also get a finite number, and so it must converge. So you see, this really mirrors what we had in the last section. Let's see how we use it. All right, so here's an example. It's kind of similar. This is meant to be a cube root of n. It's kind of similar to the one we looked at before for the direct comparison test. You might look at that and think, well, this looks a bit like the series that is just 1 over the cube root of n, right? It looks a bit like that series. So maybe we can just use the direct comparison test like we just did. Let's have a look at thinking about that, because that's an entirely reasonable way to go with this problem. If I set out an inequality here, here's the inequality that seems most natural. This is true for all n, right? For all n bigger than or equal to 1, the cube root of n is going to be smaller than the cube root of n plus something, plus 2. So this is definitely true, right? And everything here is bigger than 0. And I can rearrange this. So I divide it on the other side, and I divide this on the other side. And I end up with this inequality that's true for all n greater than or equal to 1. So it fits what we would expect. And I know that this thing's a p-series. It's a p-series with p equals 1/3, which is less than 1. So the corresponding series diverges. So 1 over the cubed root of n is going to diverge, because it's a p-series and the p-value is less than 1. So that thing diverges, and this is smaller than it, right? When I add up all the terms, in this series, here are the terms. These terms are always bigger than the terms that I'll get in that series. So what does this tell me about the series I get from these terms? Well, our inequality is the wrong way around. We found that we've got these terms, and they're smaller than these, and we found that when we add all of these up, it diverges. But these are smaller, so our test doesn't tell us anything, right? Telling you that when you add 10 plus 10 plus 10 plus 10 plus 10 for all infinity, when you do that, it diverges. That's not very surprising. And it doesn't tell you anything about what happens when you add numbers that are smaller than 10. And these numbers are smaller than 10. Well, in fact, they're smaller than these. And so this tells us nothing, right? The way this inequality is directed and the fact that this diverges, in the end, this limit comparison test tells us nothing. The comparison test, the direct comparison test, tells us nothing about the convergence of the series we're interested in. If this was a p-series that converged, and these numbers were smaller, then the direct comparison test would have said, okay, the series we're interested in converges. But because this diverged, the direct comparison test is not useful, which is why we turn to the limit comparison test. Okay, so this is what we just decided. This very similar series, 1 over the cube root of n, cube root, remember, is n to the power of 1/3. So that's a p-series with p is 1/3, which is less than 1. And so that p-series diverges. That's going to help us here, because in this case, we're going to take, and I'm going to explicitly use the symbols that they introduced in this theorem, I'm going to take A to be this quantity, and then B is going to be the quantity over here. And then I'm going to use the limit comparison test. So I've defined these terms so that they match the kind of idea we've got going on in the limit, in the theorem, and we're just going to calculate this limit, right? This is just a limit that we can do from Calc 1, and so just go ahead and plug in. And just plugging it in directly, we get something like that. And it's useful to rearrange these, because here you can see we're dividing by another fraction. So I'm just flipping that fraction up, right? If I'm dividing by a fraction, then it's the same as multiplying by the reciprocal of that fraction. So I'm literally taking this from the denominator and flipping it up. And that makes our algebra easier, right? Because then we're going to get the limit as n goes to infinity of something we can deal with. This is actually not too bad. And so I'm going to, you can do this using L'Hopital's rule, because this is a indeterminate form of type infinity over infinity in the limit. Or we can just use what we did in Calc 1 and divide the thing through by the biggest power. So when we divide it through, when we divide every term through, we divide it by there and we get 1, we divide it there and we get 1, and here we get 2 over. And because n to the 1/3 goes to infinity, 2 over that must go to 0. So in the limit, this is just the Calc 1 way of doing it, this is 1. And that's greater than 0. So these two series converge or diverge together, right? Where in this case, the limit we calculated is a positive number. And so we can use this case. And this case says they either both converge or they both diverge. Well, we saw the terms we get when we sum that limit diverges. And so the limit comparison test tells us that this thing diverges as well. Let me write that out nicely. So here's a kind of summary. We used these symbols for A and B just so that I can use those symbols. And then we found that the limit of that ratio was a positive number. It was 1 in this case. And we also found that we had a divergent p-series for one of those. So when we added up the b sub n's, we got a series that diverged. So what that means is, because we're in this case, and one of them is diverging, then they both diverge. And so we conclude that the series we're interested in, the summation of 1 over 2 plus the cube root of n, sorry, coughing fit, that must diverge as well. And that's essentially how we use the limit comparison test. I'll do one more example of these. All right, in this case, we've got something that's a real mess, right? You can start plugging numbers in there and you can calculate the terms in the series and it's going to be beautiful, absolutely beautiful. But what we're going to do is use the limit comparison test to work out what's going on here. Because what the limit comparison test is really doing is saying, there's a lot of fluff here, but at the end of the day, it's the overall power for really large values of n that's the most important thing. What's the biggest power? Because that will dominate the convergence, right? What's the dominating power when n is large? So let's give these things some names. I'm going to call a sub n just the nth term in the series we're interested in. And then we need to take b sub n. And so looking at this, we've got to take the term that's biggest when n is large. So what I'm going to do is look at it and I notice that there's a 5 here and there's an n cubed. And when n is large, the 5n cubed is going to be much more important than those things. Right? When n is large, the n to the 9 is going to be much more important than the plus 4. So I'm even going to ignore the 5. I'm going to take the n cubed in the numerator, and I'm going to take the square root of n to the 9 in the denominator, and I'm going to take that to be b. Right? The 5 is not going to matter here. What that comes out to be, we can simplify, right? This is n cubed divided by n to the 9 halves. So what's that? If I was going halves, this is, I'm going to cancel 6 of them, right? So this is 1 over n to the power of 3 halves, if I got that right. And the beauty of that is that we have a p-series. The sum of the b's, when we add up all of those terms to get that series, that gives us a p-series. And in this case, p is 3 halves, and that's bigger than 1. And so the sum of the b's converges. And when it comes to the limit comparison test, that's the thing we need to know. We need to know whether the sum of the b's converges or not. Because then we're going to build the limit as n goes to infinity of that ratio and work out what's happening to everything else. Notice I'm taking my advice from last time and I'm immediately writing this as a sub n multiplied by 1 over b sub n. And I haven't taken the nicely simplified version of b sub n. I've taken this. And I'm taking the original form because that's what I'm going to use to simplify. Because I'm going to go through here, I'm going to take this n cubed, and I'm going to divide everything in the numerator by the n cubed. And I'm going to take this n to the 9, and I'm going to divide everything in the square root by n to the 9, because I can write it like this. Right? I'm just shuffling terms around. I'm dividing the polynomial by the polynomial and the root by the root. And in fact, I can do more. I can put those under the same square root. And so when we take that limit, we could think of it as an indeterminate form, or we could just, again, do the calc 1 thing. If I divide everything on the top by n cubed, I'm going to end up with a 5, a 2 over n squared, minus 1 over n cubed. And those last two go to 0 in the limit. And then inside the square root, I'm dividing top and bottom by n to the power of 9. And so I'm going to end up with this, 4 over n to the power of 9 inside the square root. And so I can just plug into, or not plug in, but I can evaluate that limit because I know that those two terms go to 0, and I know that that term goes to 0. And so what we're left with is 5 plus 0 minus 0 multiplied by the square root of 1 over 1 plus 0, and all of that works out to be 5. And that's a number greater than 0. And so the sums of the a's, the series that I get by adding the terms a sub n, and the series that I get by adding the b sub n, do the same thing. So laying that all out, with our choices for a and b, the terms we want for the series, the simplified series that we got, we found that that limit was greater than 0, and so we can apply the limit comparison test. And combining that with the idea that the sum of the b's is just a convergent p-series, we find that the series we're interested in converges. So we can just write out that the sum of the a's, the series we're interested in, it's a convergent series by the limit comparison test. There's been a lot in the exercise today. I really encourage you to go have a go at some web work, practice these. Come talk to me if you have questions. I hope you're doing well. I'll see you next time. Bye.